Welcome to Module 14 of the Six Sigma Institute's Lean Six Sigma Certification Curriculum, which follows both the Council for Six Sigma Certification and the International Association for Six Sigma Certification bodies of knowledge. A full copy of the Council for Six Sigma Certification's Book of Knowledge can be downloaded from the course description section for free. In this module, we will be discussing the analyze phase of the DMAC methodology. This module will take approximately 60 minutes to complete. At the end of this module, there will be a 5-question quiz on the topics discussed, which you can complete on your own at any time. You will also find several Six Sigma tools that you can download, including a Fishbone diagram template, a box plot template, and a regression analysis template, all of which are Excel files. One of the fundamental activities of the analyze phase, which is performed by the entire team with the help from identified subject matter experts, is the root cause analysis. In this section, we are going to discuss the root cause analysis, which is used to identify root causes for problems or defects when a team has reached the analyze phase without a clear idea of primary causation. Some of the tools that we will talk about, which are used for identifying root causes, can be used in either the define or measure phases at the discretion of the black belt leading the team. The failure mode and effect analysis we discussed previously could likewise be used in the analyze phase as part of a root cause analysis. Kaoru Ishikawa was a Japanese organizational theorist and a professor in the engineering department at the University of Tokyo. He was known for his quality management innovations. He is considered a key figure in the development of quality initiatives in Japan, particularly the Quality Circle. Outside of Japan, he is best known for the Ishikawa or cause and effect diagram, which is often used in the analysis of industrial processes. After he became a professor in the engineering department at the university, he introduced the concept of quality circles. Quality circles is a concept that began as an experiment to see what effect the leading had could have on quality. Quality circles would soon become very popular and form an important link in a company's total quality management system. A popular method for brainstorming and analyzing causation in a process is the Fishbone diagram. The Fishbone diagram can be completed by a single Six Sigma expert, but it typically has more value when it is completed by the entire Six Sigma team. The diagram lets teams concentrate on a brainstorming process that generates ideas about possible problem causes, organizes those possibilities in a logical way, and lets teams visualize the information to identify priorities, trends, and relationships between ideas. When used as a team activity, the Fishbone diagram encourages participation and input from all team members, which increases the chance of laying the foundational work for a viable and original solution. The cause and effect diagram is also called the Fishbone diagram because you begin with what looks like a simple drawing of a fish skeleton. In order to conduct a brainstorming session, we start by sketching a basic fishbone shape on a whiteboard or large flip chart and writing a problem summary where the head should be. Draw a spine and 4 major connectors. Label each connector as people, process, materials, and procedure. Note that there are some places where various categories will overlap. Begin with each category on the fishbone diagram, asking the team how something in that category might be responsible for a problem or defect. You can use sticky notes to write down ideas and place them on the fishbone diagram so you can move ideas around later. Use the 5 whys, and for each branch of the diagram, ask why, at least 5 times to ensure the most granular detail possible. Once the team has run out of ideas for the first category, move on to the next category and move causes to the appropriate categories if needed, and don't forget to remove causes that don't prove to be valid after initial discussion. As a team, Decide which root causes seem most likely or highest priority. Circle those causes as high priority possibilities for further investigation. Once teams identify possible root causes, they must verify that the causes are valid. Root cause verification can be completed via a variety of methods, including statistical analysis, design of experiments, logical questioning, observing a process, gathering additional data, analyzing data via graphical representation, and mapping processes at a more granular level than accomplished in the defined phase. Whatever method is used to validate root cause assumptions, the Six Sigma team should document it. Documentation regarding root cause verification is usually completed on a matrix that includes the problem, possible root causes, the verification method, why the verification method was chosen, results of the verification, and, in some cases, whether a senior Six Sigma leader, such as a master or black belt, agrees with the discussion. Six Sigma experts and teams can use a variety of graphical analysis tools to help generate ideas about root causes or understand how inputs and outputs really impact each other. In this section, we are going to discuss several common tools used for graphical analysis, like the Pareto chart and box plots. Some of the more complex graphical analysis tools require statistical analysis software, which we will talk about later. These tools can be created in Excel, which costs a lot less than a licensed Minitab. The first graphical tool for validating root causes is the Pareto chart, which we discussed previously. It is based on the Pareto principle or 80-20 rule, which states that 20% of the causes lead to 80% of the results. Because of this, a Pareto chart is a good starting point for root cause brainstorming. Teams can start with the few inputs or attributes accounting for the bulk of the Pareto chart. Just as you can drill down using the fishbone diagram, asking deeper and deeper why questions, you can drill down using a Pareto chart. After creating a chart and identifying the vital few, the team could use various methods for digging deeper into these causes. They might perform a fishbone diagram to discover why the problem is occurring. If you don't have statistical software, you can create a basic Pareto chart in Excel. Now, it may take a few extra steps to create than it would using a program like Minitab, but at $1,600, most people can't afford to purchase their own copy. To create a Pareto chart in Excel, we start by creating a column for the data labels. Pareto charts work well when you have quantifiable causes for a defect or other effect. No matter what type of data you are using, enter it in order from largest to smallest for Pareto chart purposes. Next, we need to create a column for the count where we enter the total for each cause. Then we create a third column for the cumulative count, which provides a running total. Finally, you create a fourth column for the percentage. You do this by dividing the individual count for the row in the second column by the total count of all the rows in the second column. So now that we have a table consisting of 4 columns, we need to first make sure that the data is listed in order from largest to smallest, with the largest in the first row and the smallest in the last row. Then we can highlight the reason or defect, which was our first column, and the percentages column, which was the last column we created. These will be the data points used by Excel to create the Pareto chart. With those columns highlighted, we need to choose the Insert tab from the top ribbon in Excel and locate the Charts section. There you will see several options like column charts, bar charts, pie charts, and more. Make sure that you choose the chart that has the vertical bars or columns. This is an automated process that uses your default format and settings. But this will only create the chart automatically, as the trend line will need to be added manually to the chart. We accomplish this by selecting the Add Chart element from the Format tab and select Trend Line. You will have several options to choose from, and each will create a different look to the chart. But In creating a Pareto chart, it is recommended that you use either the exponential or linear trendline design. Data labels are only slightly important. After all, we are trying to decide which root causes have the greatest impacts. So, to do this, while you still have the chart selected and can see the Chart Format tab, we need to select Add Chart Element again, and this time choose Data Labels. There are several options to choose from, but make sure that the labels are legible. It is recommended that you either choose the option for outside end or outside base, and refrain from using any of the inside options as the text will generally be obscured by the bar chart. Box plots, which are often called box and whisker graphs, are another graphical representation that can be handled with Excel. In later modules on statistical analysis, we will cover how box plots can be related to hypothesis testing and other analysis. When differences between distributions are marked, however, or when outliers are fairly obvious within data, the image of a box plot tells its own story without requiring advanced statistical knowledge. A box plot begins with the upper and lower hinge, the top and bottom of the box. The top represents the 75th percentile, the bottom represents the 25th percentile of data. The line within the box represents the 50th percentile. Within the box, there are 50% of the data points between the 25th and 75th percentiles. Each box plot receives upper and lower whiskers, indicating the range of most of the other data within the set. In this case, box plots are useful in comparing how variable attributes impact a process. Six Sigma teams might compare process results for different operators, different times a day, different teams, or using different inputs. Let's go ahead and create a box plot using Excel. For simplicity, we will just use the example from the book that you can download in the course description section. We start with two sets of data that we will be comparing with one another and place them into two separate columns with headers at the top of each one. Highlight all of the data, including the headers, and click on the Insert tab at the top of the ribbon. Choose Statistical Chart and select More Statistical Charts. Box plots are hidden because they are not as commonly used as the many other charts that are available in Excel. After clicking on More, you will see a pop-up that has two tabs. The recommended charts, which are the most common ones that you will see in the menu selection area. Make sure that you have the All Charts tab selected and scroll down till you see the box and whisker. Go ahead and select it and click OK. Once you click OK, the chart will be created automatically using the default formatting. You can then change the chart using the standard chart editing functions, which can be found under the Format tab when you select the chart. You can also edit the title and data labels for your chart if need be. Through statistical analysis, companies can make good use of big data for greater success through the collection, organization, and critical examination of data in order to draw a conclusion. In this section, we are going to take our first real deep dive into the concepts of statistical analysis, including hypothesis testing, correlation and regression analysis, as well as design of experiments. We will cover many more statistical analysis tools in greater detail later on in your training though. Hypothesis testing lets Six Sigma experts draw conclusions about the population based on statistical analysis performed on a sample. Because the conclusions are based on samples and not the entire population, there is always some risk of error. You might have seen or heard poll results given with a plus or minus in the result. 60% plus or minus 2 percentage points would vote for the candidate today. That plus or minus is the value for risk. In statistical analysis, the risk that a sample doesn't offer a good representation of the population is known as the alpha risk and beta risk. Using information about the sample and alpha and beta risks, statisticians calculate what is called the p-value. The p-value is a probability estimate that tells statisticians how likely an assumption or conclusion drawn on the sample will be incorrect. Statistical software removes a lot of the manual calculations from the process of setting up and running hypothesis tests, but they can also be done using Excel. Regression and correlation analysis helps Six Sigma experts understand how variables within a process might be related. Regression analysis helps teams define relationship between one independent variable, possibly an input, and one dependent variable, possibly an output. Does the temperature of the oven have a relationship to whether the cake is baked correctly, and how close are the two related? Does the number of hours a person work have an impact on his or her productivity, and can the team show a correlation between lower production as employees approach the end of a shift? These are the types of questions that regression analysis can answer. To work with regression analysis, both the variables being studied have to be in numerical format. Correlation and regression analysis doesn't always provide the information a team needs to determine relationships between variables, especially when those relationships are complex or multiple variables are present. Because the analyze phase sets the stage for the improve phase, teams have to be as certain as possible in their analytical conclusions before they decide on solutions for implementation. A design of experiments can provide the more granular details and analysis required for that level of certainty. Design of experiments, or DOE, is generally performed via statistical analysis software such as Minitab because of its ease of use. But teams can set up experiments for one factor or multiple factors using Excel as well. You will find many useful templates that have been already created using Excel to help you conduct these and many other experiments and hypothesis testing from the download section. Once analysis of the problem or root causes of the problem are complete, Six Sigma teams usually move on to the improve phase. Again, a Tollgate review is conducted between phases. To complete the analyze phase, you must have ensured that all primary root causes have been identified and that the team has prioritized them. You will need to make sure that any assumptions regarding the root causes are backed by statistical data and that the relationships between all of the variables are fully understood and confirmed statistically. After all of this has been completed, it is time to meet with the project champion or sponsor and provide them with your findings. Once they agree, then they will sign off on the phase and you are free to move on to the implementation phase of the DMAC process. In identifying the primary root causes, you most likely used a fishbone diagram and have found that there are many different causes, so you need to narrow down that list. To do this, you then used a Pareto chart to narrow down the list to the vital few that are creating the most impact on the problem. With your list of causes, you separate the vital few from the other causes and prioritize them for improvements, either in this project or save the non-primary causes for future projects. While it is a rarity that you will find only a single root cause to a problem, this does happen from time to time. In most projects, however, we will find many different root causes, and so we need to prioritize them based on the impacts to the process, and even their impact to other processes. Just because improving a cause will positively impact the process you are working on does not mean that it will have the same impact on all other processes down the line. Sometimes, an improvement in one process will be detrimental to another process further down the line. Because of project scope and the need for results, we want to prioritize only one or two root causes that have the most impact on the process we are working to improve, but will not hamper any other processes. Before you can begin the improve phase, you need to finish the analyze phase. and that requires an approval from leadership. That means you will need to have the project champion or sponsor sign off. You will need to present the status of the project to the sponsor or champion, which means root causes need to have been identified and narrowed down to the vital few, and that you can explain the reasons behind the prioritization chosen. If there are any issues, they will need to be rectified before the champion or sponsor can sign off, and before you can begin officially working on the improvement process. Remember that in Six Sigma, we back up all assumptions with statistics. So you need to be methodical and find concrete cause effect evidence for root causes. Remember, you should not ignore the importance of treating symptoms for short term relief, while at the same time, you should also focus on correcting and remedying the root causes rather than just the symptoms. Always provide enough information to inform a corrective course of action and consider how a root cause can be prevented or how it can be replicated in the future. You should have conducted a correlation and regression analysis to ensure that you understand the relationship between the variables within the process. This is done by using correlation and scatterplot matrices to measure these relationships. This allows you to identify the correlation between the root cause and the problem with the process, as well as identify causes that are not related to the problem. Through a correlation and regression analysis, you will be able to determine whether that correlation is strong or weak and whether it is positive or negative. And of course, always remember that you need to verify everything with statistics. The major difference between Six Sigma and virtually all other quality programs and methodologies is that we seek to conform to the scientific method, and that requires all decisions to be verified with statistics. In the analyze phase, we will start with a fishbone diagram to create a list of all possible causes, and then we narrow down that list using a Pareto chart, leaving us with the vital few. Then we use a verification matrix to ensure that the cause is valid to our project and process before conducting a regression analysis in order to visualize the cause and effect relationship. When that relationship is complex, we may even conduct a design of experiments in order to see if there is a relationship between the variables.